Good afternoon, everybody. Thank you for joining us today for another EI Live K-12 session. This is actually going to be our last EI Live K-12 session for this academic year. And we will continue with these in the fall with a new lineup. We hope that you will continue joining us for these. If this is your first time, welcome. My name is Cassie and I work at the Columbia Climate School. And we are actually the first school at Columbia, or first new school at Columbia University in 25 years. And we're really excited to be bringing together experts and working on a very important issue of climate change. Many of our researchers and experts have been with Columbia University for a long time as part of the Earth Institute and particularly Lamont-Doherty Earth Observatory, which is where our speaker for today, Frank, works as a research scientist. And we're hoping that these EI Live K-12 sessions allow our experts to share various aspects of their work with a broader audience, from K-12 students to teachers to families, and anyone just interested in learning more about the work that our scientists do. So today we are going to have Frank. He's going to talk about the natural history of the Hudson River. We're recording everything, and we'll be sure to send out a recording to everyone who has signed up. During the session today, if you do have questions, we're going to be using the Q&A box and not the chat box. So just remember that. And if you do have questions throughout, feel free to pop it into the Q&A box. I'll monitor that and make sure that we get to those questions. So Frank is going to speak for a little bit, and then we will turn it over for Q&A. So Frank, whenever you're ready.
Yeah, thank you, Casey. And yeah, welcome everybody. So as she said, I'm a research scientist. My name is Frank Nitsche. I'm a research scientist at Lamont-Doherty, the Earth Observatory. And I've been actually working on the Hudson River for, on and off over the last like almost 20 years. And today I'll give you a little overview of a bit of the history of the Hudson River, like how it was formed and how the shape and the unique geography of the Hudson River influenced kind of like the European settlements along the river. And on the other hand, like how all these settlements and developments along the river actually also has an impact on the river itself. So if I'm going to start by just showing you these basically morphological map of the New York State and the Hudson River itself. So the Hudson River here is this long blue band running north-south, basically. The different colors here, different elevations. You can see it follows this kind of, like in green, the low elevation valley, the Hudson River Valley. And it's like bound on each side from basically part of the Appalachian mountain ranges, the Catskills here, for example. And just as a definition, so we talk about the Hudson River. So it has, this shows the watershed of the Hudson River. And a watershed is basically, the area where you can imagine like every raindrop that falls into the watershed will end up in the Hudson River. So all the little creeks in this area will basically drain into the Hudson River. And we kind of divide this in three parts. So there's here what's called the upper Hudson River, and the boundary here, and then the lower Hudson River, which is the estuary part, and the boundary here is around Troy. And then we have also the Mohawk branch, which is a big tributary river that flows into the Hudson, also near Troy here. Hudson River is very long. It's river, it's in kilometers, so that's like the estuary part is basically 180 miles, 240 kilometers, and the total length, it's winding up here a bit more in Upper Hudson, is almost like twice as much. And one specific thing to know is that the lower Hudson is actually tidal. So the water level is not fixed because it twice a day with the tides, basically the water level rises by 5 to 6 feet in some parts. So that's and then we'll talk about it a little later. Like that's why we call it an estuary. So how did the Hudson River form? So I'm not an expert in deep geology, but to give you a little idea. So if you look, and this is a geological map of the New York State and surrounding areas, and I don't really want to go into detail of the different rock types. You see that each color is a different rock type, but it's pretty easy to recognize that, you know, here that's basically where the Hudson River is, here in the center. So west of the Hudson River, we're having, you know, the rocks, the bedrock has a different kind of shape and texture. We have this big bulge of rocks here, and then we have a different kind of rocks on the other side. So the Hudson River basically formed where there's like two different types of rocks. So because there was like a boundary with different rock types, there was like a weak zone. So we can, if you look just in the Manhattan area down here, you can see that we have like very old hard rock in the Manhattan Bronx area. There's some softer glacial sediments on Long Island. And then we have some other sediment rock and some volcanic outcrops in the New Jersey side, the Palisades cells. But anyway, the main point I want to make is, so there's like this two different areas, and basically because it's like where different types of rocks come together, there's sometimes a weak zone, and this can be exploited by or used by geological processes. And the main process for forming the Hudson River was likely the glaciation, the ice ages. So a couple of million years ago, probably like, you know, around 3 million years ago, in the northern hemisphere, big ice sheets started to form, and then they grew and shrank and grew and shrank for the last, roughly like bit more than 3 million years. And the last glaciation, the last ice age, reached its maximum around 20,000 years. And this shows here everything in, basically you have to imagine everything here in this white color was a big ice sheet. So all of this area was covered with, in some places like over a mile of ice. And the boundary is right here, so you can see it across Long Island and New Jersey. And the ice is then flowing, like, you know, from the center of the ice sheet to the outburst, to the terminus here to the end. And because it was flowing, it was like at the bottom of the ice, it's like eroding. And there was this weak zone between the different rock types. It basically eroded the valley where the Hudson River is flowing. A little side note, if you know, how do we know where the ice was? So we can look at, for example, here at the, again, topographic map of the New York City area. So you might notice here there's this ridge that's kind of crossing across Long Island and actually continues, you know, Staten Island and into New Jersey. So this was the what we call Long Island moraine. So this is the end. This is how far the ice was advancing forward, and it's basically it's the front of the ice. It piled up a big of sediment that forms the moraine, and at that point when it was formed, it was actually like continuous here through the narrows. So this was not an open waterway. We also see that other places that there's a lot of the features have this kind of north-south tendency. So this is basically ridges and hills that were formed from the ice flowing in this direction. So we can determine from the shape of these features, like where the ice was flowing and which direction it was flowing. And if you happen to go to Central Park and look closely at some of those older rocks there, you can actually find striations on these rocks. in Central Park. Basically, this has scratch marks where the ice was creating these grooves while riding or flowing over these rocks in Central Park. So the glaciers have, shaped the Hudson Valley, but also, a lot of the other landscapes around in New York have been influenced and shaped by the glaciation and the ice flow. So what then happened, so I said like 20,000 years ago was the last maximum extent. Then maybe like around 17, 18,000 years ago, the ice started to retreat, started to melt, it was getting warmer. And when this happened, there was a lot of water released. And because then the moraine crossing Long Island and Staten Island was still intact, there was actually this water was, well, a lot of this water was caught in lakes. So the Hudson River Valley basically filled up with these big lakes, and it deposited a lot of clay material, like glacial flour, basically, that was transported with the glacier. And the lakes existed for several thousand years until roughly, I mean, this like 12, 13,000 years ago. And one of the theories, I think the more interesting ones here, is that maybe around this time, the ice retreated beyond a certain point. There was like big glacial lakes, proglacial lakes, where we have now the Great Lakes area, basically. There was one big called Glacial Lake Iroquois, and around like somewhere between 12 and 13,000 years, the ice retreated and opened a pathway here. And a lot of those waters then flew, maybe in a very catastrophic flood, through the Hudson River Valley. And at this point, the idea is that maybe this big flood kind of breached through the narrows here and opened the pathway of the Hudson River. And then the glacial lakes basically emptied out. At that point, like 12,000 years ago, you have to imagine that the sea level was still much, much lower than it's today. So when we have basically ocean sea level equivalent in the Hudson River, that was, much, much lower. And the whole Hudson River system became a river that was flowing out. And then only after then, the rest of the ice was melting, and then sea level was rising, basically maybe around like between like 8 or 10,000, 8 and 6,000 years. Maybe the Hudson River, the river got flooded by ocean water, and it created the estuarine conditions that we have today. We can see the different phases if you look at the cross section along the Hudson River. So this is one was created when they investigated the old Tappan Zee Bridge. You can actually see here that the brownish tones are the old bedrock stones, and here the valley has the glaciers dug deep. Again, this is 200 meters, so roughly 600 feet into bedrock. So the original Hudson River Valley that was carved out by the ice was much deeper than the Hudson River today. So in the Tappan Zee, the Hudson River today, maybe like 30 feet deep, maybe a little deeper in the main channel. So it was carved out much, much deeper at that point. And we can see here in the bottom, it's all lacustrine clay. So this is sediments, very fine clay that deposited there when we had all these glacial lakes in place for a couple thousand years. And then we had the breach, and then the whole system turned into a river, and the river brought a lot of sand. So we have a layer of sand on top, in some places on top of the clay. And then the system became an estuary, and we have a finer sediment, basically mud. So if I talk about, estuary, just to explain what it means. So then, when an estuary is a system where we have basically river flow, freshwater flow from one side, and then from the other side, from the ocean side, we have salt water. And because everything is at sea level and subject to tides, the tides can push the salt water into the into the estuary, like towards the river, and we get this mixing of ocean and river water. And one important characteristic is that because salt water is denser than fresh water, the fresh water is usually on top of the salt water, and the salt water is kind of forming kind of a wedge. We talk about it when we call it the salt wedge. And the whole system moves back and forth with the tides and also with the different seasons. And it has also an impact on the sediments. So we get in the river part, we still get a lot of sand transported down river, and we get sand coming in like from the ocean. But in the central part, where basically the fresh water and salt water mix, and we have a lot of turbulence and a lot of fine particles get trapped there, and there's a basically we have like muddy sediments, and these muddy sediments also cause basically the water to look very muddy and brown. So if the water looks muddy and brown in the Hudson River, it's mostly like natural, because we have this mixing going on from and this trapping of the fine particles. When I came to Lamont like 20 years ago, I got involved in studying the Hudson River. We had a big project funded to the New York State Department of Environmental Conservation to really study like habitats and in detail the distribution of different sediments and shapes in the Hudson River. So we used a lot of acoustic systems, and we basically used sonar to measure the depths in great detail, and also not only like as you can see in the graphics here, we can sonar works by sending out an acoustic pulse and listening when it comes back, and from the time it takes, you can calculate the depths. But from the strength of the signal, we can also get some information about what type of sediments are in the bottom. And we combined it with a lot of sediment cores and grabs. And good. Oh, I see there was a quick question about how far north is the salt wedge. It changes. So usually with the season, so the salt wedge usually reaches in the spring when there's a lot of fresh water up to basically Tappan Zee, Piedmont, Tappan Zee Bay. In the summer when it's really dry and there's very little river flux, it can go through the Hudson Highlands, Haverstraw Bay, Hudson Highlands, and then in very, very dry conditions, salt wedge might go even, into Newburgh Bay, when that's a time when people in Poughkeepsie and some other towns upriver that actually use river filtrate for water get a little nervous because they don't want to get the salt water coming all the way there. But usually that's the range. So Tappan Zee to the Hudson Highlands. Just continuing, so we did one of the acoustic systems we also use is looking into the sediment, so we can see different sediment layers and where things get eroded over time and where we see deposition, and understand the long-term changes of the sediments in the Hudson River a little better. And we also make combine all the information to get a really nice three-dimensional picture of the Hudson River. That's again, it's a Tappan Zee area. That's the old bridge here, and we can see here, for example, some oyster beds sticking out on the area, and then we can also see that some parts are relatively shallow, and then we have a main deeper channel in the Hudson River itself. One other results that we had was yes, we can look at the sediment type when we find the pattern that I described earlier. So this is the Hudson River because it's flowing in 3 panels. So on the northern part, we see a lot yellow here sand sediments, and then near Troy even like gravelly on the bottom, and then it changes south of Kingston to green, which is mostly muddy sediments, and we have mud dominated almost until we get back to the harbor where we have more sandy sediments again. So we have this pattern of sand from the ocean, sand from the river, and muddy sediments in the estuarine part in the middle. And yeah, the salt wedge, just to show again. So if it's really, fresh water can get, usually the lowest is in this area, the salt wedge, but it then in the dry summers goes all the way up here and can even reach up here in very dry summer conditions. But this is a normal range where the top of the salt wedge is. But the whole range up to Troy is tidal. You have fresh water, but it's still going up and down. We also take sediment cores. For example, here, so this, if you, that's basically we're taking a tube and taking a long slice of sediments out of the river bottom, and then because there's cores, they record basically what happens with sediment over time. We get a record of how the sediments and maybe how also the conditions in the Hudson River have changed over time. So for example, here you can see different layers. So something changed at this interval in the Hudson River, and sometimes we get some approximate dates. For example, looking at the chemistry, there's different ways to get dates, but one way will be used where you can measure like the cesium content. So this is very, very small amounts, but because when they did nuclear testing in the 1950s, there was a little bit of cesium-137 released in the atmosphere, and this settled down all over the world. And then you can measure this very small amounts, and basically we know right here when we start to see an increase, that maybe that's when the atmospheric nuclear testing started in the around 1950s, and then they stopped in the late 80s, late 60s somewhere, and then there was also some accidental release at Indian Point in 1972. So we can use this as a trace marker to see that's modern sediments. And in addition to this, we can also use other elements. So one that we use a lot is lead, for example. There's a lot of lead from industry, but a big uptake was actually with the introduction of gasoline for cars. In the 1930s, there was this peak, and in the early times, gasoline had a lot of lead in it, and the fumes from the atmosphere, and this then settled down in the river, and we can trace this in the sediment. And here again, the peak was in 1970 around. I think 1972 there was the Clean Water Act, and then also lead was banned from gasoline, and we saw the drop off in lead in the sediment since then. So that was a little bit about what we work on the Hudson River and how it was formed and how we measure it. So I was not, just seeing like how it impacted the development of the Hudson River in general. So we have today like over 20 million people living in the watershed around New York City and along the Hudson River. It is still like combined New York and New York is like the 3rd largest port of the US. There's a lot of commerce going on, results a lot of contamination, and there's also now a lot of restoration efforts, sea level going on. But it's a lot of development that all of these impacted the Hudson River over time. But if you go back how it all started, I mean, the Europeans were not the first people, of course. Here there was very vibrant Native American population living along the Hudson River. There was a lot of like fish here, and in the lower part, oysters that were harvested and fished by the native communities. And this all changed then, of course, when Henry Hudson discovered the Hudson River and sailed up the Hudson River. It's happened in 1609. And it's also a good side project if you want to get an impression how the area looked. And when Henry Hudson sailed up the river, how Manhattan looked. There's this project, Manhattan Velikia, that kind of tries to reconstruct how New York City looked at that time. Of course, a lot of things have changed since then, and this all had also an impact on the Hudson River. To see how basic the geography of the Hudson River also influenced like the development and settlements with the Europeans, then it, I just want to go back to the morphology. So as I showed earlier, Hudson River was created by the glaciers, and this kind of put in the unique position that all of this, basically all of this Hudson River all the way to Troy is basically sea level. It's very flat, I mean, it was originally even carved out deeper than infill, but this is basically all sea level here. And because it's estuary and it's tidal, you don't have to row up, you just have to wait for the right tide, and then boats can move up and down the river pretty good using the tides, pretty easy, not much of an effort. Certainly much easier than taking a cart or horses and go over the mountain ranges that you have on the other side. And a good example, I mean, the Hudson River, this is also where a lot of towns and formed early on, just, on both sides of the Hudson River. And another nice map that illustrates like the economic, like special locations that New York had is this railroad map that I found somewhere, basically shown, after the mid-19th century, like, and when the railroads kind of started taking over from the boat traffic, it was also much easier then, of course, to build a railroad next to the Hudson River, where it's basically sea level. You don't have any large inclines that go up and down. So you could actually build the trains along parallel to the Hudson River and then follow the Mohawk, and then you basically get to the Great Lake areas. And then, this opens up to the Midwest, Chicago, Detroit, and so on. And because this, was a very easy to build railway lines and trade lines, New York became this big hub commercially, where basically, you kind of makes this connection between like Europe and the ocean going world and whatever happened in all the Midwestern areas. All the goods were exchanged along this route. Much easier to go this way than going over the mountains. And so this is like, I think, a big reason why New York became this big commercial center of the United States. With a big center and a lot of development that happens as a result, there were a lot of changes on the Hudson River itself. So the geography impacted the settlement, but all the settlements then had an impact basically on the Hudson River itself. And there's one, if you look at old maps, I like old maps, it's really great to see the difference. So we have this old map here from 1766. And I put in the same projection as this aerial image here from the present, and you can see, it looks very different. East River is much wider in the past than it is today. Hudson Rivers and much different. And if you even look at Governor's Island, it was much smaller than what it's today. And we can map out the difference, and you can see how the shoreline has changed. A lot of this is being infill and putting out piers further to the deeper water areas, the edges of the Hudson River. And Manhattan is always short on space as well. So a lot of things have changed there. But it was not only Manhattan, there was also happening similar changes up the Hudson River. So this is near Albany. So until the late 1900s, we had the river was they're actually not as straight, but had a lot of like little islands and bifurcation, and was sometimes getting shoulder. Things were changed. So it was not really good for navigation, especially when boats and barges became larger. So it was actually artificial straightened. So a lot of the upper part of the Hudson River is actually not natural, is straightened. And if you go there at low tide, you can actually see, so it was done around 1900. And you can still see old ridges of wooden pilings that they put in to make basically the edges of the Hudson River, and then had put sediment on behind them. In addition to putting the pilings, they also had to dredge. So it's a lot of sediments were dredged out of the Hudson River, and mostly in the upper part. So there's a lot of dredging going from north of Kingston and then all the way to Albany, Troy, and then a little bit in the harbor. A lot of the Hudson River in between Kingston and Manhattan is naturally like deep enough for most boats. So I think the goal is to keep it to around 30 feet in the main channel. Smaller changes that we see is, for example, here, even like just putting in a bridge can alter the bottom or the bed of the river a little bit. Doesn't have a big impact as a dredging and channelizing, but you can see that here, that wherever we have a bridge piling, so this is near Poughkeepsie, you can see there's like ridges of sediment that are forming behind it, and in between it gets like deeper because the water gets pushed through these pilings, and then it gets scouring a lot some of the sediment. And we can see this in our sonar data as well. And we see like areas where sediment is depositing and piling, and then others where it might be scouring off. Another side remark I want to do, so it's like random pieces here. So this is up the Hudson River. This is the North River treatment plant, the wastewater treatment plant at around 134th Street, I think, in Manhattan. And this is the detailed like sonar image of the bottom of the Hudson River. And little fun fact here, you can see the outflow pipe in the sonar, and where the water is coming out, it scours a little bit of the sediment. But the main reason I want to show this picture here is also that it was built 1980, in the 1980s. And before that, a lot of northern Manhattan did not really have a sewage treatment plant. A lot of the material was basically dumped in the Hudson River. And it's a lot of things is like, it's still some problems with that in some places when we have a lot of rain and the treatment plants cannot keep up with this, what is then called combined sewage overflow. But it's city has been very active to improve the situation for many decades, and it's gotten much, much better. In the past, for example, this is some estimates from the researchers from the sediment load of the Hudson River in the 60s. And you can see, so the total load of the Hudson River is like 800,000 tons of sediments, and some of the smaller rivers and that also go to the New York Harbor area, maybe another 100 tons here. And this is also what the river sediment load is today. But then they found and estimated there was another 270 tons, so basically a third of the what the river bringing itself was basically sediment, or what do you call sediment, like stuff that came from a sewer system that was dumped directly into the Hudson River. There was a lot of basically wastewater and solids that came with the wastewater dumped into the Hudson River. It was a really, really big problem, and it's been continuously cleaned up. It's much better now, but it was a big impact on the Hudson River at that time. Another thing, so we did a detailed sonar. So we do, because there's a lot of ship traffic still, so sometimes ships sink, so we can see a lot of shipwrecks on the Hudson, which is a very nice. I just like these images, so I'd like to show those, but it's a little side effect. But it's also an indication that it has been a lot of traffic and over many, many decades and centuries. Just briefly towards the end, so there was like the human impact, but then as some of you might remember, in 2011 we had the storm Irene, and then 2012 there was a Hurricane Sandy. So there's a right that said, big natural events can also have a big impact on the Hudson River system. I'm just going to briefly show the impact. So this is 2 images, one before Irene on the left and one after Irene. And I go here about Irene, which did not cause so much flooding in New York City than Sandy did, but it caused a lot of rain and flooding in the upper state, and it actually brought a lot of water and scoured a lot of sediment into the river. So the estimated input from Irene is basically 3 times the annual load of sediments was brought in like 2 weeks. So over the year, maybe we get like 700,000-800,000 tons of sediments that flow through the Hudson River system with Irene. And there was another storm, Lee, before that. Together, they brought in 2.7 million tons. So a lot of sediment dumped into the river. And you can see from the pictures, like how the water looks normally here on the Coast Fault. Then during Irene, it's just loaded with sediment. The river is brown. And was also an event, by the way, where the salt waste was pushed out all the way to Manhattan because there was so much fresh water in the system. And we took some sediment cores afterwards and just quickly show, we can actually see all this sediment, this brown layers here in the sediment core. So that's a marker in the sediments, and see, like, get an idea like how much sediment and where the sediment got distributed to. Another aspect that's more looking out in the future is we have to deal with sea level rise. Another student looking at, for example, Piedmont Marsh, like how would sea level rise impact some of the marsh systems in the Hudson River. And marshes can grow over time when sea level rise, but she found here that yes, that if we get like low level of sea level rise, the marshes might be able to keep up. But if sea level rise gets too far, that's like over, I think, a period of 100 years, you get like a 1.5 meter, then Piedmont Marsh would not be able to keep up and be submerged. So something else that might in the future play a role, how the Hudson will be shaped in the future. All right, there was a very brief overview, different elements like how the Hudson River was shaped mostly by glaciations, and then how European settlement followed the geography that was created through the glaciations, and being a long fjord, and that has basically sea level with tides and not just a down current. But then we saw also that the settlements had impact on the Hudson River itself, and there's impacts of big storms and sea level to come. And this is all I want to show, and then thank you for your attention. And I have a little movie at the end from the harbor to show you the bottom. While this is running, I can start answering some questions. So the Hudson River, how long is it? It's, as I said, 500 kilometers. So that would be like maybe like 280, 300, not quite 300, 280 miles. The estuarine part, the tidal part is 180 miles, 240 kilometers. It's pretty long. And I think the question like, where does it go? Probably means like, where does it come from? I'm guessing. So it comes from the Adirondack Mountains. I think there's a Lake Tears or something where it originated, like a small, if you go there on hiking, there's some areas where you can just step over the Hudson River, and and then it gets wider and wider. I don't know if this was the question. Anyway, thank you, and if there's any other questions, let me know.
Great. Thanks, Frank. Let's open it up. If there's any additional questions, feel free to use the Q&A box. Frank, I've got a question for you. You've done, you've studied the Hudson, and our viewers may not know that you've also done many cruises and in Antarctica as well. And so I'm curious to hear from your point of view, what why, I guess, waterways are of particular interest to you, and some of the similar techniques, or some of, maybe it's similar tools that you use, but just perhaps if you could share a little bit more about your work in this area.
Yeah, sure. I think there's like two parts of, certainly from one side is like the tools are the same. So I'm like a geophysicist by training, so do a little bit marine geology and geophysics. So we basically taking sonar to map the bottom of the ocean. I do this around Antarctica, and but also Hudson River here, and we take sediment cores. I think I like to say just the ship is a little bigger if you go down to Antarctica. We take small boats on the Hudson River here. So I think a lot of the techniques are similar. So this is how I got involved. But then, I think what I'm looking at in Antarctica is also like understanding how the glaciers have been were flowing in the past, and where they were out on the continental shelf, how the glaciers retreated in the past in Antarctica when it was getting warmer, like 15,000 years ago, what happened to the glaciers there. So if we understand how the glaciers behaved in the past, we might be able to predict how the glaciers might behave in Antarctica in the future. And then there's a linkage here. So the Hudson River was also formed by glaciers, and there's a lot of features that are actually quite similar. Well, maybe not in the Hudson River, but like in the surrounding land, that is similar to features we see also around Antarctica. There's this, and another connection that's happening often is, so what happens to the glaciers in Antarctica will have an impact on sea level rise here, and this will have an impact for the future of the coastal areas in general.
That's great. Thank you for that. We have a question, which will probably actually be our last question here. Does the Hudson River, this is a great question, I love this. Does the Hudson River have a twin somewhere in the world? Is there another river perhaps with a similar history or geography that you might be aware of? Yeah.
There might be some other, so we get some other rivers that have estuaries, but it's kind of special in a way that it's this long elongated. You find other rivers where this estuarine portion is much shorter. Mm-hmm. There's other, I think it's what's special is here is a combination, like how it's been the area eroded and how it's set into bedrock. I mean, if you go through the Hudson Highlands, it looks very similar to some fjords in Norway in terms of the shape. On the other hand, you see other rivers and also like in Germany, others that has, Thames River that have a bit of a glacial past too, and they have an estuarine component. But I think usually the estuarine side is not doesn't go so deep. So I think it's kind of it's kind of special. There might be similar ones, but I cannot think of many that are really that similar. So it's kind of unique in a way.
Great. Right in our own backyard too.
Yeah.
Well, thank you so much, Frank, for your time, and thanks everyone for tuning in for your questions. Frank, is there anything else you want to share with the audience for further interest or reading, or any last words?
No, I mean, if somebody is interested, if like, people from schools are listening in, they can definitely reach out to me, and if they have questions, I'm happy to answer. It's fascinating to go and spend many weeks surveying on the Hudson River, especially go further out north from. I mean, it's very interesting in New York City to see the city from the river for once, but if you go up the river, it's really beautiful, and I think that's quite good.
Yeah. Fantastic. Well, thank you so much for taking the time to share a little bit of your work with us and the history. And for our viewers, as I mentioned, this is our last EI Live K-12 for this academic year, but we will be returning. If you have any additional questions for Frank or about any of our other sessions, feel free to get in touch with me. You have all received my email reminding you about the session. We'll share a recording with you, hopefully by the end of this week, if not by very early next week. And with that, hope you have a great afternoon or evening or morning, wherever you are. And thank you so much for tuning in, and we'll see you soon. Thank you, Frank.
Yeah, thank you. Thank you for listening. Okay, bye-bye.
Bye.